In this video, we'll be going over the learning objective, deriving the equations of uniformly accelerated motion. Start with a nice velocity time graph. All right, so on the horizontal axis, we're taking a look at time, measured in parentheses seconds. And over here, this is going to be velocity measured in meters per second. All right. An object that starts with non-zero velocity and uniformly accelerates. Stand by. From initial velocity u to final velocity, let's say this was the final velocity right here. V. Okay. So we use u for initial velocity, v for final velocity, and this object increased its speed from u to v over time t. All right. So this is the setup. Something like that. We just discussed a moment ago, if we're already going this fast, and we just go at uniform, constant velocity, no acceleration for a certain amount of time, that we just multiply velocity times time, we get the displacement, okay? So that was taking the area underneath. We said that the other thing that we could do is calculate the slope, the rise over the run, and that's going to give us units of meters per second, change in velocity, over seconds of time, we get meters per second squared, so that's acceleration. So the very first equation that we can derive here is going to be using the definition of acceleration, and that the rate of change of velocity, right, the change in velocity over the change in time gives acceleration. So we'll say that acceleration A is equal to the change in velocity over the change in time. You should have it memorized that acceleration is the rate of change of velocity. That's the way that you should remember defining acceleration. The rate of change of velocity. The variables that we use in this class, we've got v minus u over t. Okay, so the change in velocity is final minus initial. That's how you calculate a change. Divided by t, because t right here is 0. Right, so we have a true 0 right here, then t minus 0 is just t, so we get this. Rise over run. Meters per second, right? So meters per second squared are the units that we get. We want equations of motion that don't contain negative signs, that don't contain fractions. We can avoid it, and so we're just going to do some algebra here. Let's rewrite this like if A equals v minus u over t, just kind of put these back together again. Multiply both sides by t to get rid of that fraction right there, and we end up getting at equals v minus u. And then we added u to both sides. Gotta add u to both sides. And we have our equation 1, which would be v equal to u plus at. No fractions, no negative signs. That's a good way to think about equation 1. V equals u plus at, where u is the initial velocity, v is the final velocity, a is the acceleration, and t is the time. We're going to derive 4 equations that relate 5 different variables. The variable that's not contained here is displacement. Note that we don't know anything about displacement in that equation. We can't solve for it. We can only work with those 4 variables that are there. Okay, so that's equation 1. Remember also that v minus u is equal to at. Remember that. Let's get back to this idea of the area now. We'd already said that if we're not accelerating, we're just moving along at constant velocity for a certain time. The displacement, we use sour lime chalk. S, right? Sour lime. Displacement equals velocity times time. Okay?
What's the variable for displacement?
S. S for displacement, right? Makes sense. It really comes from the Latin word spatium, space. So, you know, the space something has traveled. I had to look it up one year. I'm like, why S for displacement? You know, I was curious enough to actually look it up. So the Latin word spatium, like the space, okay? And that makes sense. Like, okay, yeah, we covered some space, you know, some physical distance in the universe here if we travel at a speed per time. So this would just be the non-accelerated part of the motion. We cover a certain amount of ground by virtue of the fact we were already going this fast before we sped up, okay? So that's the area of this rectangular part, okay? Now we need to add in this triangle. If you know the area of a trapezoid, I think there's a formula for it. It will agree with what we're about to derive here. Like I suppose you could solve this with the area of the trapezoid. All right, so let's go to this triangle now and realize, hey, there's some extra displacement, some extra ground we've covered because we've sped up, right? We didn't just go U the whole way. We went U, and so there's some displacement from that. Like if we didn't speed up, we would cover this much. But we did, you know, increase our velocity, so there's extra ground to cover here. I always like to think of the practical example of if you're speeding up from like a residential street to a highway, an engineer might want to calculate like how much distance do I need to build this road so that cars can safely like bring themselves up to speed, right? So there's always a practical sort of utility of this of saying like, okay, cars are going about 35, we're going to speed up to 70. How long do I need to build this road so that most cars, you know, are going to be able to do that, you know, comfortably. So we're going to get some displacement here, right? So another term for displacement from this triangle. So it's a triangle, so 1/2 base times height. So we're solving for the displacement when we take the area. We're going to use 1/2 the base. So what is the base right here? It's v minus u, right? Just like we did rise, you know, when we did the slope calculation, it was the rise, which is the difference between v and u. So v minus u is the base. But what is v minus u? AT. So I said, remember that. So I'm going to describe this base as acceleration times time. That's the base of this triangle. What's the height of the triangle? T, right? So we got 1/2 base times height. Okay, this 1/2. The base is AT, the height is T, so it's 1/2 AT squared. So what's a good equation to solve for displacement in uniform acceleration? Remember, these equations only work when I have uniform acceleration. Okay, we're deriving these from a graph like this, uniform acceleration. That's why they're called that, the equations of uniformly accelerated motion. So I have equation 2, S equals UT plus 1/2 AT squared. At the end of chapter 2, there's a learning objective that requires you to describe projectile motion in terms of horizontal and vertical components. And the range equation, like how far away something lands, is just this part of it, because gravity only affects things vertically. So when you fire a projectile, its range is equal to Vxt. Like that's just sort of taking this part of the equation and saying, oh, when the acceleration is 0, that term goes away, right? And I just got sort of this part of it left. And so we can sort of pull out, you know, other equations like, oh yeah, distance equals rate times time, right? So this is just like the familiar, you know, or just even the basic definition of velocity, you know, kind of similar to this, that remember that velocity is just displacement over time. So I could rewrite that as S equals VT. It's UT, right, the initial velocity, but that's just rewriting the definition of velocity to make displacement the subject. Okay, this is the part of the area that's not accelerated, but I got to add in the extra displacement from acceleration. So you have 2 terms. Both of them will be meters, right? So when I take like meters per second times seconds, I get so many meters here of displacement. When I take meters per second squared and acceleration and multiply it by seconds squared of time, the seconds squared are going to cancel. So like this term gives me meters, this term gives me meters, Meters plus meters gives me the total displacement for something that is undergoing uniform acceleration from u to v over time t. Equation 2, last final velocity, right? So every one of the big four relates 1, 2, 3, 4 variables. They omit, one of them. In this case, there's no final velocity. In this case, there's no displacement. All right, on to the next one. We need blue chalk for this. So we're going to say, yeah, we sped up from u to v, but can't we just say we were going like this speed on average out our speed from u to v? Because then we got a simpler shape to work with. All right. So we want another equation that gives us displacement. We're going to take the area underneath this blue line now, this dashed blue line. You see that, YouTube? You see a little bit more clearly. All right, so that line has what value? U plus u over 2. Just the average of u and v, right? So I add them up and divide by 2. So this value is u. Here's 0. Here's u. Here's v. That's the average of u and v, right? U plus u over 2. What's the area underneath this blue line? Length times the width. Okay, what does the area underneath the velocity time graph give us? Displacement. So I got the length, v plus u over 2. I'm going to write it like this. Okay, same thing, right? V plus u over 2, or I could like factor out a 1/2, v plus u or u plus v, doesn't matter where you want to add those. And then length times width, right? The width is still t. So the area of this sort of blue rectangle, okay, is just saying, let's get rid of acceleration. We're not accelerating, right? We just sort of average it, right? So see how there's no acceleration in this equation? That's the one that's omitted. We're just we're moving at a constant velocity equal to the average of the two speeds that we actually sort of, went from this speed to this speed. So that's why it becomes like a simpler sort of area problem. And you might think, well, but wait, we started at this speed. We didn't really cover this area or calculating, right? But this area here is the same as this area here, right? So not the way I drew it, or not the scale, but you get the idea, right? Like we only took this area. Well, we didn't account for this, but we did add this back in, and then we do the same. Okay. You did it on graph, we're going to feel clear that that's the case. All right, so far so good. We've got equation 1, sour lemon chalk. Got equation 2, sour lime chalk. We got equation 3, and sky blue chalk. 3 S's. Sour lemon, sour lime, sky blue. Now we need equation 4. Equation 4 will omit time. Time. We need an equation with no time. We got to substitute for time. If I rewrite this equation using the old algebra switcheroo, okay, that they teach you in algebra class, where t equals v minus u over a, right? Anytime you see things like this, you can just switch it. Multiply both sides by t, I'll put it here, and divide each side by a. Maybe that's easy. If I divided both sides of this by a, I get this, right? But t is equal to v minus u over a. So I'm going to plug that in for t here. Okay. So instead of writing t, I'm going to substitute what it's equal to eliminate it out of the equation. So I'm going to rewrite equation 4. This is where I blew it last time. I think I got plenty of room here. I feel pretty good about this now. All right. So we're going to say. S equals. All right. I'm going to rewrite this one like this. U plus v over 2. So I've got S equals u plus v over 2. Yeah, okay. Times time, but remember what time is equal to. Time is v minus u over a. So that's what S is equal to. Do you want to call that one equation 4? No, YouTube knows it. No way. We gotta do some more work on this. We don't like fractions, we don't like negative signs, and we don't like this kind of, doesn't seem like it's simplified enough, right? Okay. How do you multiply fractions? Numerator times numerator gives you a new numerator. Denominator times denominator gives you the new denominator. It's not adding them, right? You don't have to have common denominators. It's simpler to multiply fractions than to add them. So I always like to tell students, I'll take care of the denominator. If you guys take care of the numerator, fair, good. 2 times A, 2A. You're welcome. Now you guys get the fun part. Multiply the numerators out there. How do you multiply two binomials? You want to FOIL this? You could FOIL it. FOILing is just distributing, right? You're saying U times B is U times negative U is negative U squared. B times B is B squared. And B times negative U is negative UV. So that's just FOILing those binomials or distributing, whatever you want to call it. UV minus UV, 0. So I end up getting the displacement equal to negative U squared plus V squared over 2N. The same thing we did up here. We got rid of fractions, we got rid of negative signs. We want to do with this one. So if I multiply both sides by 2A, this will become 2AS equal to, I'm going to rewrite this like this, B squared minus U squared. Right? This is the term that's negative, this term is positive, doesn't matter where you add them. And then get rid of the negative sign by adding U squared to both sides. So we end up getting our final equation 4, which I want to write down here. 1, 2, 3. Equation 4 is going to be B squared equals U squared 2AS. So there is no time in that equation, right? This is the equation that relates final velocity, initial velocity, acceleration, and displacement. We'll call that one equation 4. All right, so that's how you derive the big 4 equations. All right, we start with a velocity time graph. You understand that the slope gives acceleration and the area underneath gives displacement. And then you can do some, little tricks like, oh, let's just average this to eliminate, the acceleration variable. Let's substitute in what time is equal to get an equation where there's no time. So these are good to sort of have memorized. You do get equations 2 and 4 on your list of formula. You don't have to memorize it. You'll list the formula when you sit for the papers, and these ones are included. Sometimes it's helpful to know the other 2, though. So this is like the definition of acceleration. That's important to know, right? It's a separate learning objective. So we get more out of these equations than we kind of put into them. It's like just by sort of doing some examination of this graph, now we got 4 very general equations that are very broadly applicable. So we can always apply if there's constant acceleration. Gravity is a constant accelerator. So when we examine free fall, studying gravity, these equations, become very important.